So today we're going to talk about similarity statements. So let's get this going. Page 75, similarity in CSSTP. Okay, let's book it. Alright, so here comes the fun part. You will need a blue and green marker, so grab that if you don't have it. Alright, so page 73, or excuse me, 75. And 75? Did I say 75? 75. Alright, our objective is to use similarity statements to identify corresponding angles and proportionate sides. Okay. So we talked about isometries in the last unit, and all isometries are similar. So what does similar mean? Let's get our blue marker out here. And similar means same shape, same angles, not same size. So two shapes are similar if they're the same shape, same angles, but they are not same size, not necessarily. I'm pretty sure I spelled that wrong. Please feel free to spell that correctly. Okay? So, however, this is the big caveat here. All sides have the same proportion that's our scale factor to the preimage. So what that means is I could have a triangle or some shape that's the same shape where the angles are all the same. Okay, if this was 1, 2, 3, then this would be 1x, 2x, 3x, where x is a scale factor. So that's x times as large of a perimeter as this one. Okay. So all images and preimages of an isometry are similar because they have a scale factor of 1. Okay. All images Because remember, all isometries, the image and the preimage is congruent, so the scale factor would be 1. And preimages of dilations, which are not an isometry, are similar. Because dilations, remember, keep the same slope and the same angle measure. Okay? So we have a little bit of different notation for similarity than we do congruence. So let's say I had two shapes. Okay. Let's say I had 90, 45, 45. Okay. And I had another shape. Also 90, 45, 45. Ooh, let's change that one of those. Let's change that 45 to 40 and 50. 40 and 50. Okay, because I want to be able to differentiate between the two. So when B and E are both 40, C and F are both 50. Okay, so these two triangles are similar because they have the same shape and the same angle measure. That makes something similar. And to tell the reader that they're similar, I'm going to use this notation. I'm going to say that A, B, C is similar to, that's like half of the congruent symbol. And again, just like when I wrote my congruence statements and my similarity statements, I want to make sure the angles match up. So what angle on this triangle is the same as angle A? Well, angle D is the same. What angle in this triangle is the same as angle B? Well, B was 40, so it's E. And what angle is the same as angle C? Well, that's F, because it's also 50. Okay? And this is our next, big theorem. And our next big theorem says that from the similarity statement, I can find two things. Well, one of them is this, that corresponding, this is in green, sides of similar triangles are in proportion. That's CSSTP. Okay. And what that means is that the sides are in proportion based on the similarity statement. So that means that AB is in proportion to DE, which is in the same proportion as BC is to EF, which is in the same proportion as AC, that's my last side, is to DF. Okay? So all these sides are in proportion, and I know which sides are in proportion to each other, or maintain this proportion, based on my similarity statement. Okay? From this similarity statement, I also know which angles are congruent. So based on the similarity statement, using the similarity statement, I know that angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F. And what this is just corresponding, not as important, angles of similar triangles are congruent. Less exciting, cast. Okay? So some really interesting things start to happen when we look at the ratios of the sides to each other. So I want to do a little example over on this side. Okay? What I'm going to do is I'm going to make two rectangles. I got two rectangles, okay? So what I'm doing is these two rectangles are similar because they have the same angles and their sides are going to be in proportion. So the side of AB is going to be 4, and the side of AD will be 5. Okay? And so this side up here is going to be, 8, and this side here is going to be 10. So the question is what happens here to this rectangle? Well, an interesting thing happens. We know that the sides will be in proportion. So I'm going to say that rectangle ABCD is in proportion to rectangle EFGH. Okay? And I'm going to say it has a scale factor, an R, of 2. Okay? So, if I know this, then I know that AB over AD, or excuse me, AB over EF is going to be in proportion to AD over EH. And if I check that out, AB is 4, EF is 8, AD is 5, EH is 10. There we go, 1/2. Right. And if I were to do this, if this is the image, and this is the preimage, I can also see where the scale factor comes in. Remember, R is equal to the image divided by the preimage. So the length of one of my image lengths, say EH, divided by AD. EH is 10, AD is 5, and I see my scale factor here is still 2. Okay, what happens when I compare the perimeter? So if I did I'm doing comparing small over large. Okay, so I'm going to start with my small rectangle. If I compared AB over EF, and I said, how does that compare to the perimeter of ABCD compared to the perimeter of EFGH? Well, A over B, or AB over EH would be 4 over 8. And I need to find the perimeter of this guy. So this opposite side would be 5, this would be 4, the perimeter would be 8, 10, 18. Here, my opposite sides are 10, 8, perimeter would be 36. So how do those two numbers compare? Well, I'll come back and I'll say what happens with the perimeter of ABCD, which is 18, and perimeter of EFGH, which is 36. Well, an interesting thing happens. This reduces to 1/2, and this reduces to 1/2. So they are equal. They are actually in proportion. So the question I'm going to leave you with is, if I do small, compare small over large again in my proportion, how does AB over EF relate to the area of ABCD compared to the area of EFGH? How does that compare? That's it. Long video, short idea. Have a great week.